a question is there. It asks that given an uniformly charged sphere of radius capital R with total charge Q, what is the electrostatic energy of the charge distribution? Given an uniformly charged sphere of radius capital R with total charge Q, what is the electrostatic energy of the charge distribution? So, the concept of electrostatic energy is needed here to solve this question. What is that electrostatic energy? The electrostatic energy is actually electrostatic energy of an assembly of charge is the potential energy of the charge distribution or the assembly of charge with respect to the condition or the state in which all the charges are infinitely far away from one another. So there is a state where charges are infinitely far away from one another, and there is another state where we have an assembly of charge. So the electrostatic energy of this assembly of charge is the potential energy associated with this assembly with respect to the state in which all these charges are infinitely far away from one another. Okay, and how come potential energy gets in the assembly of charge? Because we know we have to do work to bring the charges from far away positions to make it an assembly of charge against the Coulombic interaction. And whatever the work is done, this work gets stored in the system, which is the assembly of the charge distribution, as potential energy. And this potential energy is actually the electrostatic energy of the assembly of charge. Okay, so in this question we have a spherical charge distribution which is uniformly charged with total charge given Q. So, and we have to find the electrostatic energy of this spherical charge of radius R and total charge Q. So, what we have to do is, let there be a small sphere. We are building from very small sphere to a large sphere of radius R. Okay, so suppose we have built a small sphere of radius, say small r. Okay, now what is the charge in it? Let the charge density be rho. This is the volume charge density. Okay, so therefore in the sphere of radius small r, the charge is q equals to 4/3 pi r cube into rho. So volume into charge density. Okay, so we have the charge sphere of radius smaller and we have a surface here. So the potential on the surface of this sphere is phi, and phi is equals to what? This charge q by 4 pi epsilon 0 into r. Okay, so we have got the potential on the surface of the small sphere. Now let us bring one element of charge, say, which has a thickness of dr. Okay, so this has the thickness of dr. So what we will do, we will keep on adding such charge elements until we have a sphere, large sphere of radius which is capital R. Okay, and on that sphere the total charge will be capital Q. So when we have brought this charge element which is having thickness dr, we will have to do some work against the electrostatic interaction of this small sphere of radius r and this charge element. Okay, so the charge on this element of thickness dr, and since dr is very small, let us take this also has radius r. Okay, so the charge on this element will be what? Is the density of charge multiplied with the volume of the element. What is that? Volume of the element will be 4 pi r square into the thickness dr. This is the area of sphere of radius r, surface area, multiplied with the thickness. So you have 4 pi r square rho dr. Okay, these let us say as dq. So what is the work that we have done gets stored as some potential energy. So incremental potential energy of the system, okay, is, let's say, du. What it will be? It will be dq multiplied with the potential which was there at the surface of the sphere of radius r, and we have these values dq and phi. We substitute them, 4 pi r square rho dr multiplied with 1 by 4 pi epsilon 0 r, and q is there. We can put q as what? We can put q as 4/3 pi r cube into rho. Here we have, okay. So we can simplify this. We can cancel the same terms like 4 pi. We can cancel one r from here, and remaining any term is there. Okay, so this du is equals to, there is 4/3 pi and there is epsilon, okay, there is rho square and there is r to the power 4. Okay, so you have du is equals to 4 pi by 3 epsilon naught rho square and r to the power 4 dr. Okay, so we have to build a sphere of radius capital R, right? So we have to keep on incrementing this energy, and up to what? Up to say u. When we have built a sphere of radius r, capital R, we have energy say capital U. So here we will, and the volume charge density is constant, so we can keep it outside integration, and we are building a sphere of radius up to r. So we integrate this, it will come as, after putting the limits of the integration, it will come as r to the power 5 by 5. Okay, and this is our u, the potential energy of the charge, uniform charge distribution over a sphere of radius r. And remember, in the question it is given that the charge, the total charge on this sphere is capital Q. So when we have built a sphere of radius capital R, the total charge on it will be capital Q. So we can replace this rho with Q. How? We can just simply write 4/3 pi r cube into rho is equals to Q. Okay, and so rho is equals to Q by 4 pi r cube, 3Q by 4 pi r cube. So what will be rho square is 9Q square by 16 pi square r to the power 6. Now we can put the value of rho here, then so what is rho square? 9Q square by 16 pi square r to the power 6. Okay, and we can cancel here r to the power 5, r to the power 6, we have 1 r, we can cancel 1 pi, we can cancel 3, here it will be 3, so 4, here it will be 4. So you have, after everything, 3q square in the numerator, divide by 5, 4, 20 pi epsilon naught and r. Okay, so this is the potential energy of the uniform charge distribution of uniform spherical charge distribution of radius r containing the total charge capital Q, and this is the electrostatic energy of the system as we discussed while starting the problem. So you have the electrostatic energy as 3q square by 20 pi epsilon naught r. Okay, so I hope you have understood. Thank you.